Good afternoon and welcome to MAE 113 Calculus for the Liberal Arts. I'm Richard Kohar and this is lecture 17. And in today's lecture, we're going to cover section 3.2, increasing and decreasing functions. This is in the textbook and we'll do a little bit of review. Just a couple of announcements before we start. The test is Thursday. Please see Moodle for instructions. You must have a way to scan your solutions, and you should test to make sure that you can scan it, so either using a scanner or a camera phone. And then you need to be able to convert those to a PDF. Now, another thing is if I'm unable to read your solutions, then I'm unable to give you marks. So, now hopefully everyone realizes that we don't have a quiz today. We have no quiz. We're going to forego the quiz this week, and we have the test on Thursday. So, the other thing I should see, hopefully you can all hear me. So if you can hear me, just say so in the chat, just to make sure that you can. And I'll just ask. Oh, excellent. Okay, perfect. It's a bit lagging. Okay. Excellent. Okay, so yesterday I was talking to you about the intermediate value theorem and kind of that idea of, well, I can actually pull the sheet out for you. So we were talking about this yesterday, and we said that if f is a continuous function and it's on some closed interval, a, b, then there's some c that's between kind of the y values for a and b, such that it kind of crosses that point, and then there exists an x naught. So there's an x naught or an x that goes into that function and will give you c. So again, the idea is I have a flexi curve, and so the idea was, again, if you have 2 points here, and again, here is a continuous curve here. I can't break it. I can't do a whole bunch of weird things to it, so it's a nice smooth continuous curve. If I need to get from this point to this point, it doesn't really matter what I do. If I try to bend it or curve it, it still will cross this point. And now this line here could be an arbitrary line, so I could cross at any point. But for instance, on this point, it's crossing. Here's my A and here's my B. And so it crosses at this point right here. So that would give you, for instance, at this point, this would be my C, and this would be my x naught. And so this point right here, that would be the x naught, which equals c. Okay, so how can we use that theorem? Put that to the side. So let's just do a little example then. So if I have here's an example, and we're going to be given some function. So we're given, say, f of x is equal to x squared plus 2x plus 1. Then they ask, show that there exists some x naught such that f of x naught equals 2. So what's kind of okay? I can answer that question too. So, there's a question in the chat. It says, in reference to the exam, will it be printable? Yes. So you can print it off. There will be space for you to fill it in, and you can write on it and do whatever. So you can print it out at the start and ignore the computer until the end. Exactly. Yes. If you don't have a printer, what you'll be asked to do is to write it out on blank paper and then scan it. You'll have to check, you'll have to look at the PDF that I give you, and you'll have to scan blank paper. Okay, so again, we have this value function, or this intermediate value function that we need to look at. And in this case, we're not given some. Is there going to be added? Yeah, so you'll have 50 minutes for the test, and then there's 10 minutes at the end. So you can scan it. So the faster you're done, the sooner you can leave to go to your next class. Okay. But again, instructions all on Moodle. We'll talk a little bit more when we get to the portion of this lecture when we start to do a little bit more review. Okay, so I have this example. I have a function. I'm asked, what's the x naught where this function equals 2, and I'm not given an interval. We just need to show that it exists. It doesn't actually say find it, which is kind of weird in math because we're used to saying like find x, find x, and you usually see the meme like, oh, there it is. That's not what we're doing here. We're just trying to prove that it exists. So we don't have an interval, so that's a bit odd. What we can do is we could pick one. And I'll pick, let's pick an interval. So what we're basically doing is when we're picking that interval, what we're actually doing is we're setting up those kind of barriers that we had, right? We had the A and the B. Yes, line paper is fine. I mean, it should be clear enough so that I can read it, right? You can use line paper, you can use grid paper. Basically, don't start writing it on a takeout menu. I can't read that. It has to be clean. It can't have, coffee stains on it. Make it look professional and presentable. And again, the more stuff, the cleaner the paper, the less likely that there's going to be like artifacts when they're scanning due to aliasing. So I'm going to pick an interval. So I'm picking those barriers, right? If I think of this as my C and I have my points, I have my sum function. Again, I'm thinking of it like the border crossing or the foosball kind of idea. So I'm going to pick an interval. Let's say, let's pick that interval, and we're going to do, say, closed, and we're going to look at 0 and 5. So what is that value at 0 for this function? Well, putting 0 back into the function, I have 0 squared plus 2 times 0 plus 1, so that gives me 1. And subbing 5 into the function is going to, so what this is doing is I know that this is 1, this is 5, and the value of this is going to be 5 squared plus 2 times 5 plus 1, so 25 plus 10 plus 1. So I have 35 plus 1 gives me 36. So for here, I have 1, and up to here I have 36. So I've kind of made my box now. So I have a box like this that I've kind of enclosed, and that this continuous function has to cross. Now, what else is important about the intermediate value function? Another assumption that f has to satisfy is that it is a continuous function. So this function is continuous because it is a polynomial. So I'm going to say, since f is a polynomial, this implies f is continuous. And since 2 is in that interval, therefore by the intermediate value theorem, it guarantees the existence of some x naught of f of x such that okay. So sometimes you'll see that this is a theorem. For instance, in math, there's things that we call existence theorems, which means that, for example, this intermediate value theorem is called an existence theorem because it's showing or demonstrating that there is an existence of something. We don't actually find it. And another thing that's common in analysis in mathematics is uniqueness. So a uniqueness theorem would say that there is only one of something like that. Now, what's interesting with this is I should mention that it guarantees an existence of it. Now, it doesn't actually say that there's only one of them. So I got to make sure this theorem does not say there is one and only one x naught. Meaning that, yeah, actually, in fact, if you pick any c here, you could actually have something where the function kind of, could go back and forth a couple times and then get to that point. So you can see that it's crossed several times. And, sometimes just knowing that it at least crosses once is good enough for us. So in math, we'd like to do it, at least one or two ways. And the reason for that is, we've got to make sure that we know what we're doing. In this case, though, what we could actually do is actually find that point. So since we actually showed that it exists, we should be able to find it. Kind of like a treasure map. We know that it exists. We know that the treasure exists, so we should be able to find it. So what that is actually saying then is, well, I'm going to roughly kind of sketch this out. So I have something like this, and I assume it's some sort of parabola. And, it's between, we were looking at 0 and 5. And here is like, say, my 2. So it has to cross at some point like that. So what that is actually saying is we're looking for its equivalent to, finding where f of x plus 1 and g of x equals 2, where they intersect. Intersect. There we go. So what that is saying is we have we have x squared plus 2x plus 1 equals 2. And we'll bring the 2 to the left-hand side, so I get x squared plus 2x. 1 minus 2 gives me minus 1 equals 0. Okay. Now this is a weird one. We can't actually factor this one. So what we'll do now, we'll pull out the sledgehammer. So using the quadratic formula, what I'm going to do is, so in this case, my A is equal to 1, my B is equal to 2, and my C is equal to minus 1. And again, just saying it out loud, minus B plus or minus the square root of B squared minus 4AC all over 2A. And now I just kind of simplify. I have 2 squared is 4. And then I have a minus and a minus, which gives me a positive. That's 4 over 2. So what I have is 4 times 2. Square root of 4 is 2, and then I can't do anything with the square root of 2, so leave that. Divide by 2. Now I can divide by the 2, so that I'm left with minus 1 plus or minus the square root of 2. So then the value that we want is actually f of minus 1, and we'll because we've got to be within that interval of 0 and 5 that we were looking at, it's going to be minus 1 plus square root of 2. Now if you're really worried about that, hopefully I remember what the square root of 2 is. It should be about 1.414. But, just to double check. Yep. So again, so that's the square root of 2, and then you have a minus 1 to deal with, so you add that, and you've got 0.4142. So you're within that interval of 0 to 5. So that's good. And then I guess if you really wanted to prove to yourself, you would have f of minus 1 plus square root of 2 equals. So I'm substituting that into that function, x squared plus 2x plus 1. Now notice too, as I'm writing on blank sheets of paper, I'm always numbering pages, because sometimes people it happens, but sometimes the papers kind of get jumbled up as you're scanning them or something like that. So if there's something that goes awry, I should be able to figure out the order of the pages. So again, you can just substitute those values in. So again, we have it squared, so I have a minus 1 plus square root of 2. So expanding that out, you'll have 1 plus a minus square root of 2. Then you'll have a plus square. No, you'll have a minus. You'll have a so just a second. There's the minus. And then in here, that's also a minus. And then here, this is a square root times a square root would give you just 2. So I can substitute that in. So I get 1 minus 2 root 2 plus 2. And then over here, I'll have a minus 2. And then I have plus 2 root 2 plus 1. Okay, so I have the 2 root 2 is a minus here and a 2 root 2 here, so that cancels. I also have 2 minus 2 here, so that can cancel. And so I'm left with 1 plus 1, which equals 2. So that's a good way to check. So that's good. So this is, I'll just write that this was our check. So sometimes we don't actually have to find it, we just have to know that it exists. And so instead of doing all that work, if we check in on a couple of conditions that, first of all, that it's a continuous function, that it's we have some closed interval that we're working on, then if we pick some value within that, then we can actually show that there exists an f of x naught which equals that value that we want. Okay, so going back to the third page there. Now we can actually move on to the increasing and decreasing of functions. So maybe I'll actually show how this works. I'll try this. We'll see if I royally... Come on, flexi curve. There. We'll do it something like that. So you kind of have a nice smooth curves instead of my shaky hand. And so I can actually pick something like, oh, we'll do something here and maybe around here. So we can see by the graph that this is something where it's increasing. It's getting bigger as x is increasing, that the function itself, the y value, is increasing as well. And over on this hand side, so I have, like, say here, which is, I'll call it point A and point B, and here's point C. We can see that from A to B, the function is increasing. And in some books, you may see something along the lines of like an arrow kind of pointing like that. And what's another one? Oh yeah, so then we'll also say that from B to C, this function is decreasing. Okay, so that's what it looks like visually. We'll need a little bit of a kind of a mathematical way of writing it. So what we'll say is that we'll have a function f is increasing, and we'll say it has to be increasing on an interval. So it's increasing on an interval, and we'll use some sort of like A and B. So what I'll do is I'll show some points here. So I'll call this point is x1, and this is the function of x1, and I'll pick another one here. Here's x2. So we'll say that this function f is increasing on an interval if this f1 is less than x2. So it's less than this value is less than this value. You know, whenever or for all the values x1 less than x2 in the interval. Okay, so what I'm going to do again, so I'll just kind of redraw this again. Let's use some sort of downward curve. Something, I don't know. Like that. Some downward curve. And so from here, let's call this another point now, A and B. I'll say that this is x1 and here is x2. So that's the function x1, and here is the function at f at x2. And so what we'll do is we'll kind of use the same idea, and we'll just kind of replace those words. We'll have a function is decreasing. On an interval if, and this time it's going to be f of x1, and we have f of x2. And instead this time the first value has to be bigger than the second value. So then we put a f1 is greater than f of x2. And that's whenever, or you could think of it for any points, x1 which is less than x2, which is in the interval. So with these, what you'll be asked then is, you know, typical questions, which would be, where is the function f increasing on what interval, and where is the function decreasing and on what interval? So this is page 4. So is everyone okay what I'm doing so far? I think it's fairly straightforward, but if there's any questions or if I'm going too fast, too slow, I'm just having a look at the chat. sir, did you mean to have x1 and x2 at the points a and b because those are currently the ends of our interval? Let me just go back to the sheet. I'm using capital letters. If that's, I guess that could be confusing. But no, these are just little letters A and B. So again, this was kind of my definition. Oh yeah, the plot twist. The plot thickens. So this was kind of just my definition. Yeah, of course, we have to have some derivatives involved here. Why are we interested in, if we were business administrators or if we're economists, why are we sort of interested in things increasing or decreasing? Well, we want, again, know increasing and decreasing are rates of change. And maybe So in this case, this A belongs to here, and here's my B. And this is my B here, and here's my C. But for instance, here on this one, my interval would actually be probably around here. Here's my A, and around here would be around my B. Because that would be my interval where it's increasing. And around here, let's say here and here, I'm not sure where this is going to end. Maybe I should have drawn that with some sort of switch here, and we'll start increasing. So on this case, let's say around here is where it starts to decrease, and we'll say right around here is where it switches and becomes increasing. So yes, how are we going to jam derivatives into this? If you ever go to Home Depot and you start walking up and down the aisles, you start looking at the tools and you think, oh, that would be something cool to go and buy and bring home. And you buy a saw or table saw or something like that. Same thing like with calculus. Trying to find a derivative is like having a hammer in your hand. Having a hammer in your hand, the whole world looks like a nail. Somebody says about watching the leading coefficient, but I'm not quite sure about the leading coefficient that you were talking about. If you're talking about, I'm not sure. Just type a little bit more about what you mean in relation to like a leading coefficient in what function. But we'll start off with a simple function, which we all know and love, which is the parabolic to determine. I'll get to that. It's not quite a coefficient. We end up looking at the sign. We look at the sign of it. So here is my x squared. And so we can see here, which is quite obvious because we have the graph in front of us. And it's obvious because we're working with a very simple case. But again, in terms of learning math, we start with a simple case and we just keep abstracting it. So if we have the increasing, where is the interval where it's increasing? Again, that's my little symbol for increasing. Maybe I'll just increasing. Where is it where it's increasing? Well, we can see that it's on the interval, not including 0, because 0, it's not increasing. It's actually switching from decreasing to increasing. So from that point, it's not including 0, but it just keeps growing and growing and growing to infinity. So it's increasing from 0 to infinity on the open interval. And where is it decreasing? Again, it's coming down, the values are decreasing, and that's from minus infinity to 0. Now, as we were talking about it already in the chat, people are asking, how am I going to jam a derivative? Well, again, a derivative, in this case, is very simple. We know what the derivative is, because if I look at this, I take the derivative of that. That's just 2x. But we also know what the geometric interpretation is of it. So I could, at this point here, draw a tangent. So I'm trying to draw it so that it just touches. I have another one here. Right there. I can draw one right here. Not very dark, but there we go. And for people who think that I don't know how to use a ruler, the reason why I always flip it over is I'm using actually just the pen to the tip of the pen to just slide along it, and this has a little ridge on it. When I have it face down, when I pull a line with the pen, it starts to, it will have ink on the edge of the ruler, and when you go to slide it, you smear it all across the page. So I do know how to use a ruler. I just thought there was a little reason for it. So what are we noticing when it's increasing? So this is the derivative here. And if we look at the slope, again, the slope is the derivative, we see that the slopes are all positive. They're all positive when it's increasing. Yes, exactly. Drawing instruments. Yeah. We used to do a lot of technical drawings. Okay, so that's kind of what I'm going to say here. We're going to have f prime, and it's going to be greater than 0. Yes, exactly. Got to take care of your tools. If you take care of them, and they're decent quality, they should last a lifetime. Same thing on this side. When we're looking at the slopes of the tangents for a decreasing interval, we notice that these are all negative. All the slopes are negative. So again, we can say here, it's less than 0. Everyone would be like, and what about that shadowy place? That's beyond our borders, Simba. You must never go. No, we can actually go here. It's okay that we have f prime at x equals 0. And again, we have a flat tangent. And so it's a horizontal tangent. That means that the slope is 0. So then, is there something important about this? Yes. These are important. These are called I know, I gotta pull out some, I gotta update my references, my movie references. These are called critical values. The word critical is kind of the key. You'll hear critical values. Some people will say critical numbers. I think the textbook uses critical values. I don't know. And then we have, so these are critical values. So from that, all we have to do then is we've kind of developed a little test, which is we could take the derivative of the function, and wherever the derivative is less than 0, we know that it's decreasing. And wherever the derivative is wherever the derivative is positive, it's increasing. And why are the critical values, why are we interested where the values of the derivative is 0? Is because that is where the action starts to happen. So from this side, we see that it switches from decreasing to increasing. So in fact, we've kind of got, we can think of the 4 cases then. So there's kind of, you know, yeah, let's go with the 4 cases. So we have 4 cases. So maybe I'll draw, this is some freehand, not free bird, it's freehand. And from this, we can have it where it's decreasing and then increasing, which is what we kind of have right here. There is my critical value, say x naught here. So it's decreasing and increasing. So we can actually have where it switches. So this is kind of case 1. We can actually have another one right here. Say case 2 here. Have something like that. So there's kind of like your critical point right here. So it's switching from increasing to decreasing. The third one, we can have it decreasing, go flat, and still decreasing. So you can actually have a decreasing, and here's a decreasing. And I'll have one more down here. And we can have it increasing, flatten out, and increase again. Yep. So we can have it increasing here, and here is around where the kind of a critical value, and then it increasing as well. So these are critical values. We kind of can see that when we have kind of that flat horizontal tangent, that is where the action is happening. So why we are interested in something like this is this is an example of a minimum. Actually, we'll call it a local, but it's a local minimum. In this one, so why are we looking for a minimum? This function could be a cost function. So again, boss wants us to minimize costs. Okay, we're looking for a minimum now. The boss wants us to, this could be our profit or our revenue. Boss tells us maximize that. This could be a maximum. So this is a local max. And nothing, nothing. Okay. Let's do page 5. Let's do some examples. That over here. Those critical values look a lot like, yes. So there can be some things that are called inflection points. Yep. But we get to those when we look at the second derivative. The second derivative is what we start to look at. You know, we have things are increasing, but you know, when we start to look at the rate of increasing, then that's when we're getting to the second derivative, and that's where we have something where we're switching from the rate of increasing is increasing to. We'll get to that. I'm trying to not let out the word concavity, but so we have, where is the function? And we're given y equals x cubed plus 6x squared plus 9x plus 2. Where is the function increasing? So without sketching this, I kind of know that this is a cubic function. It's you know, it'll have some sort of shape to like, kind of like that. Something like that. But without me actually drawing it, I don't know where the intervals are actually, they're increasing and decreasing. So I have a dy by dx. So what I'm doing is I'm taking the derivative. So it's 3x squared plus 12x plus 9 okay. Then the next one is, this is the question Maria should be asking. Should we simplify it? Yes, we need to simplify it at this point. We are going to factor this. So I see that I have a common factor of 3, so I can actually pull that out. Oh, and why? Yeah, and why do we need to simplify it? Is because we need to do some more work with this. We need to find where the critical values are. So that's actually what we're doing here. Find the critical values. Now I know that I was usually writing where I was used to writing f prime of x equals 0. But in this case, it's where we've got a y function here, so it's dy by dx. So I am going to find the derivative. So I'm going to factor this out. And again, I can simplify that, or sorry, I mean factor it. So what we need to do to find the critical values is where it equals 0. So 3 So this equals 0 when one of these are 0. So if x plus 1 equals 0, then that means that x was minus 1. And if this term was 0, because again, if any of these terms, like this term here or this term here, is 0, then the whole thing is 0. So again, that's why we factored it. So now I have -1 and -3. These are my critical values. So what I've drawn here is my kind of number line. And it doesn't have to be super accurate. It's just something for me to, like a table or something like that. But it just helps me to kind of, just to, drawing diagrams in general is a good thing. So in math, I'm trying to come up with a diagram so that I can figure out some of the information I know and I don't know. So here's x equals -3. Here is x equals -1. And again, these are my critical values. So this is where it's potentially going to be changing from increasing to decreasing, or, you know, it stays the same. So what this has done is I've broken up now the real line into 3 intervals. What I have is from the -infinity to -3 interval, I have a -3 to -1 interval, and then I also have -1 to infinity. And so what I need to do is I need to figure out and this is also equivalent to my dy by dx. I need to figure out on this interval here, is this positive or negative? Is this positive or negative? And same thing, is this positive or negative? So the way to do that is pick a value. Let's say, so this is my value here. So I'm going to say pick a value and let's say at x equals -4. So then at x equals 4, that means I have 3 times -4 plus 1 times -4 plus 3. That equals 3 times, so -4 plus 1, that's -3. And I have -4 plus 3, so -1. Minus and minus gives me positive, so that should be 9. Since this is increasing, or sorry, since this is positive, so this means that the function is increasing on -infinity to -3. Then I can pick some other point here. Let's pick, it has to be a point between -3 and -1. So I'll pick -2. So I have 3 times, and then -2 plus 1. -2 plus 3. Then I have -1, 1, and so I'm left with +3. No, minus. There we go. There we go. So that implies that it is decreasing on the interval -3, -1. And then we have x equals 1. Oh, no. I'm going to do this much more easier. 0. I'm going to pick a 0. So I got 3 times, and then I have 0 plus 1 times 0 plus 3. So that gives me 3 times 1 times 3. So 9. So that is positive. So that's increasing on minus 1 to infinity. So again, that's kind of our number 2. So number 2 is test values of the derivative to the left and right of the critical value. And that's what we're doing. I've just tested a value on the left-hand side. I found out that it's positive. On the right-hand side here of minus 3, I saw that it's negative. And on the right-hand side of minus 1, that is positive. So I actually have this function here is increasing, it's decreasing here, and it's increasing. So what I will do here is we should answer what the question was. They wanted to know where it was increasing. So we should answer that. Therefore, the function y is increasing on minus infinity comma 3 union minus 1 to infinity. The other thing that we can do is we can also say that at x equals minus 3, we see that it's increasing and decreasing. So around that point, right there, it's a local max or a local maximum. And as we're going from here to here, at the minus 1, this is a local min. So what I've done there is, maybe I'll draw a little, so here and here, what have I done? I have classified so I can classify the critical values. And this is something that I kind of get for free when I'm doing this kind of question, which is increasing. So yeah, while it says to find the increasing intervals, you can't find the increasing intervals without also finding the decreasing. And because you're finding the increasing and decreasing intervals, you also find out what the behavior is like around the critical values. So again, that's kind of the free information. Let's do another example. So this one says, find the intervals of increasing and decreasing of the function it's a little different. Just a second, I'll just kind of answer that, because there's kind of two things that when we're looking at increasing, when you can have two kind of things. You can have something where it's increasing like this, and you can also have it where it's increasing like this. So again, there's two behaviors. Here's 1 and 2. They're both increasing. But this one is getting like increasing faster, and this one is increasing slower. So again, this the rate of increase. So I can say the rate of increase is growing, or is increasing as well. So it's growing, and the rate of increasing on this one is slowing down. So because I'm looking at the growing and slowing, which is I'm looking at this now as a rate of increase, now I'm getting into the second derivative. So the second derivative helps tell me kind of this shape. Is yes, it's increasing, and that's what the first derivative will tell us, but the second derivative will tell us if it's growing, like the increase is growing, or if the rate of increase is slowing. But it's a good question. We can use that second derivative, and that's what the next part is we're going to do. Not today, and not on Thursday, but probably the following Monday. But they're good questions. So same idea. I can find the derivative. Again, these questions could get more complex if it's not a polynomial. Like you could have a rational function, so then you'd have to still differentiate that. And then you could have something where it involves using the quotient rule, and you'll have to simplify, and eventually you'll have to set that equal to 0 and solve for those critical values. So that's where the simplification of equations comes into play. Right, so I start talking and then I forget what I was writing. So now what I can do is I can pull out the 4x here. And that I can still factor. Oops, no, it should be a minus. I'll do it properly. I just have to switch pens. The tape doesn't work very well with fountain ink, so. That's equal to 4. And so that means that this derivative is equal to 0 when this is equal to 0. This one right here is equal to minus 1. And this one is equal to 4, positive 4. So same idea again, just as a kind of a way to break, just to do my table, basically. So now instead I should have a minus 1. I have x equals 0. And then I actually have x equals 4. So now instead of 3 that I had last time, I actually have, I think I have 4. Four intervals to look at. And then what we do is we start picking values for that again. So let's see. F prime at 2, well, minus 2. So again, I substituted my value. So I got 4 times minus 2, minus 2 plus 1, minus 2 minus 4. So I have a minus, a minus, a minus, so I still keep the minus. And then I have 8 times 6, which is 48. So it's still definitely quite negative. So that means that it is definitely decreasing. Did I do that correct? Make sure that I'm doing my simple arithmetic correctly. We can pick a value. Okay, perfect. And let's say for here, I'll pick up minus, let's see, excellent. I like to see that people are working it along so that I'm not super fond of this one, which is I'm going to have a half or something like that. So let's do minus a half. So I get 4 times a minus a half times a minus a half plus 1, and then a minus a half minus 4. So I get minus 2 times, and then I get plus 1, so that becomes just a positive a half. And then I have minus then I have, oh man, just a second. Okay, sorry, I didn't mean, I was trying to not cough into the microphone, so I get 3 halves. So I also have 2 times a half, that gives me minus 1. Still I get minus 3 halves, and then I get 3 halves. 4.5. Did I mess up? Let's do that minus. I'll actually. It's negative a half. I got 3 halves. Oh, now we're at 50-50, so someone else has to break the tie. So I got a I got 3.5, yeah. Yeah, I still got 3.5. Okay, perfect. I subbed positive. Ah, yes, right here. Thank you. So that should be 4.5. Excellent. 4.5. 4.5. Perfect. Thank you. So that's positive. And yeah, hopefully you get to pick some nicer values now. I'm going to pick 1 prime. Thank you. Thank you, Joe. Excellent. So now we're back to integers, which is good. 4 times 2 is 8. 8 times -3 is -24. I should always, now I'm going to be defaulting to Joe to make sure that I got that one right? And then 4 times 5. Then I have 5 plus, gives me 6. And I'll have 5 minus 4, which could give me 1. So I'll have 20 times 6, which gives me 120, which again, that's positive. So I should have a negative here. So that means that this is decreasing, and here is increasing. There we go. Perfect. And again, I can classify these points. So at this, here is my min, here's my max, and here's my min again. But it asked where the intervals are increasing and decreasing. So again, it is increasing on this one, which is -1 to 0. Or it's also increasing on 4 to infinity. And it's decreasing on this one down here. And it's decreasing from 0 to 4. Okay. Ooh, time for a little break. I'm tired of the arithmetic, so time to try this. This is just a figure that was out of the textbook. Here is, I'll call this page 7. But it's a figure 3.2.12. And what the question was is match the functions and their derivatives. So the idea behind that is we're looking at where it's increasing and decreasing. For instance, my desk space is decreasing. I am quite cramped. So what I should do is grab this. So I'll use so I have these 1 So I should make this a little bit. This is 1, here's 2, here's 3, here's 4, here's 5, and this is A, B, C, D, and E. So I'll write down the numbers over here. We'll match them up. So the idea behind this is we're kind of doing that, looking at the first derivative. Okay, so on this side, we actually see that this is decreasing and that this is increasing. And the other thing too here is that we can't draw a tangent. Again, it kind of teeters. We can't draw a derivative. So immediately I know that derivative does not exist at that point. So I know that. What are some easier ones that we could do first? Oh, well, we know what this one is. Let's do this one. We have the absolute value function. And again, that derivative doesn't exist there either. We have it where it's decreasing and it's increasing here. Now we know that when we take the derivative of a flat line, or of a line here, that it's going to be constant. So we know that it's going to be right here. Since this is decreasing, this means that the first derivative is negative, and on this side it's going to be positive. So the only function that I can see here where it's negative and it's positive, so on the left hand side of the x equals 0, it's negative, and the derivative is positive on the right hand side of x equals 0, and also that it doesn't exist, the derivative doesn't exist here. See, there's some holes here. So I'm going to mark that off. I think that 4 matches with A. Let's see, the next thing is we have flat here, we have flat here, we have flat here. We also have flat here, and flat here. So what does this mean? I have it going down, it's going to come back up, down, and back up. And this one is going to be up, then down, then up, then down. So I need to look for 1, 2, 3. And the other thing that we know too is that this is a degree 4, and this is a degree 4 as well. So that means, because when we take the derivative also, we know that the degree has to go down by 1. So we have to be looking for a degree 3, which is a cubic. So this is a degree 3, or sorry, a degree 4, and here's a degree 4. And the only functions here that are degree 3 are right here, and another one right here. So 2 and 3 probably have to match with B and E. So this one is decreasing. So I would match it with this one, which is decreasing here, and then it's increasing, and then it's decreasing. So let's see. Oh no. Let's see. So that is what we have to watch. Okay. So I need to find where this point here is kind of where this is going to equal 0. So I have a point here, I have a point here, and I have a point here. And remember, this is where it's positive, which is this part right here. And this is where it's negative. So for 2, I see that it's positive. So it's positive here. And then it switches temporarily, goes down into the negatives. And then it becomes positive again, and then back into the negatives. So I'm going to match 2 with B. Same thing on this one right here. This is going down, so that means this is going down, so that means that it has to be negative. So it's starting out in the negative, so it's going down, and then it becomes positive, and then it hits 0, so there's a 0 here, and then it flips back down into the negative, and then becomes positive again. So I'll match 3 with E. And here's one where this one is increasing, and this one is also increasing. So this one is increasing and this one is increasing. And so the only thing that I can find of that means that the derivative has to be always greater than 0. So the only one where it's greater than 0 is this one, because the only remaining ones that I have, yes, exactly D. So I can cross those off. I'm left with. So is everyone okay with how I'm doing this so far? So then, by elimination, basically 1 and C have to match. But let's also kind of run through it. So for C, what ends up happening is that this is a negative. So it's going down, down, down all the way. It's going quite steep. And then on the right-hand side of x equals 0, this is positive. Now, why doesn't the derivative exist is because it's going down. It's going down, 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 down. And you're finding that the tangent is going towards vertical. And it's a negative slope. So that's why it's going off to negative infinity here. And then same thing, as we come from the right-hand side, I have this, but the slope starts to increase as I'm approaching from the right-hand side towards x equals 0. It's becoming positive. It's almost becoming a vertical line again, and it's approaching positive infinity. So that's why 1 and C match. And so there's kind of our answers for matching that. Okay. That was a lot of talking for me. Now, if you are comfortable with, if you want to try more of that, there is an exercise like that in that section. So try that out yourself and check the solutions at the back of the book. So there is I'll just say that. In section 3.2. Okay. So let's do 8. Because this is what probably everyone was more interested about was about the review for the test. Excellent. Okay, I'll put that down. Page 162. So let's do a review. I'll use oh yes. Is the I'm sorry, I didn't even see the IVT. Is it on the test? I don't think I will put IVT on the test. What I will do though is we did cover continuity though on earlier, so that is still going to be part of it because I think we covered continuity around 1.2, 1.3. So continuity will be, but not the IVT. There's a lot of stuff I got to test, so I think IVT is something. I mean, we just don't have the time. There's a lot of things I need to test. So what we were focusing on so far, what we've been doing is derivatives. And what is a derivative? Well, we have kind of two things. We have the physical interpretation. And so those are things of like rates of change, why for you guys, okay, not necessarily like the velocity or the acceleration or the jerk or the snap, crackle, and pop, but, and I didn't actually mean that is the legitimate terms for it, but probably you're more interested in terms of like marginal profits, the cost or the revenue. What is the profit I'm going to make on selling the next object? So like kind of me figuring out how much profit I'm going to make on the 1,000th bag of propellant that we're going to sell. That is what we're kind of interested in. So we have rates of change, and we're kind of always looking at over a delta y over a delta x. What's the other kind of interpretation that we've got? We have a geometric. And what is that? That's the tangent to the curve. So you can already see questions that are possible to ask. That I could ask you about velocity and acceleration. I could ask you to calculate marginal profits or cost revenue. I can ask you to find, from here, I could ask you, find the slope of the tangent. The other one is finding the actual equation of the tangent. Now, there are things that we can use to find the derivative. We have the sum rule. We have the quotient and product rules that we can use. We have chain rule. So those are things that we can use to find it. The other one is by definition of it. And to find it by definition, that's we had that limit of f of x plus delta x minus f of x all over delta x. So that's by a definition. And what leads from that is we have, well, now we have limits. So limits are kind of that key point of calculus, and it's letting things get really, really close to one another without actually touching it. First of all, with limits, we have questions of, does it exist? So again, you could be asked, does this limit exist? We also use the idea of limits for continuity. Again, we can also talk about continuity and IBT, but we're not going to cover IBT on this test. What else do we have? So we have limits, continuity, if there is existence. So those are kind of questions we can ask about that. You can also find or calculate those limits. Then the next one is I kind of have this back and forth between the integral. And this is kind of like the undo function. So we're undoing the derivative, and this is, differentiating so that we do get the derivative. So just a second, I'm seeing questions. Okay, how many questions can we expect to have on the test? I mean, the number, that's because some questions could have parts or whatever. So again, the question, you should, you will have 50 minutes to do it. And so I would budget enough time for each individual question. I know that's not a very good answer, but you can already kind of see where the questions can kind of come from. For instance, you could have a question like this. You could have a question about, the application of it. You could have a question about finding the tangent. There's about 5 with sub-questions A through Z. I mean, you're going to have to, yeah, I mean, you can kind of see there's like maybe 1, 2, maybe 3, 4, 5, 6, 7, 8, maybe 8. I don't know yet. I'm kind of looking at it and I'm judging it by that. Could we be asked to do proofs? Could we be asked to do proofs? Why not? I would focus on something where it's easy to prove, some rule, or to prove something that it exists is something like this here. Again, it's quite possible, yep. Even we did a proof where we were showing that f and g, if we took two functions f and g and we multiplied them together, that the individual function f, I should write this out. We had shown that f and g were continuous, and we actually showed then that f and g were itself continuous. So it's possible. There's proofs, yes. But the proof should be, basically to understand certain rules that I'm trying to test you on. So for instance, the proofs for the sum or the product rule kind of tests your rules of limits. This is another way to test if you knew your limit laws. Will there be anything on chapter 3? There's continuity. Yes, there is continuity, so part of that. But don't expect too much from, we're not going to cover the IVT and we're not going to cover increasing and decreasing. That's a good question. Do you know why each section writes different tests? Each section writes different tests because they are catering to different types of students. And in this section, we're catering to the business administration and the economic students. So the tests are tailored so that you have the amount of your rigorous amount of math behind the tools so that you should be successful in your upper year courses. I hope that answers, if that's a satisfactory answer. Yes. Yep. Because in business admin and economics requires a heavier... like I said before, I made the joke that an economist is essentially a mathematician that can win the Nobel Prize. That is... there's a lot of math behind it. And same thing with business administration. And they do rely a lot on calculus. And as you get up in higher levels, you're going to get into courses where it's optimization. And when you get into courses like optimization, again, you get into not only calculus like this, but you're actually going to get into like not only just one variable calculus, but you're going to get into multivariate calculus. And if you don't have the foundations for one variable calculus, it's very hard to have those expectations of students to extend that further to 2 or 3 variables. Yes, there is a rhyme and a reason for most of the things that we're doing. And we should be fairly... we'll do this through Zoom. It will be invigilated. And I expect there to be some... Well, hopefully it'll be smooth. I do ask that people show up a couple of minutes early so that we can, first of all, check your setups to make sure that we can see the desk and make sure that there's nothing around you and so forth. To be able to show your identification cards and to kind of go through the rules of the test. And then you'll have a solid 50 minutes of writing time. And then at the end, you stop. You will scan it, and then you will, upload it through Moodle as a single PDF with your name and your student ID number and the course code, and that's how we'll mark it. It's usually there is a reason for it, for why we're doing things. Why are we doing it invigilated? It makes it easier to... the questions can be easier because if it's not invigilated, it means that people could be looking up stuff online. They could be looking stuff up in the textbook. And that means that the questions then have to be harder. So that's what we're trying to avoid. The reason why we're not using calculators is because it makes the questions simpler. Again, if you're allowed a calculator, then I can ask more complicated functions. And again, pen, paper, ruler. I'll let you have a ruler, and because I can't draw straight lines, so it might help you for when you're doing something like this. But I think we've hit our mark. Let's see. Yeah. 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 I know, right? You catch me on an off day and not enough caffeine, which almost is like, it's like almost every day is an off day. So, but since I have about, sir, on the invigilation setup, the computer is on the side, but if I cannot print the test, can I have my computer in front of me to see the, yes. You'll be able to look at the questions. Now, this is the key point. You are allowed to momentarily touch the computer so that you can advance to the next question. But that is all. You shouldn't be typing. If you are using a phone, make sure that you switch it to Do Not Disturb, because I did my first invigilation over Zoom last week, and for instance, somebody's phone wasn't set to Do Not Disturb, and so it starts to buzz, it starts to ding, and everyone else is on the call, and you're not muted. I have to be able to hear everything, so again, that can be distracting to other students. So again, it's not for probably switching it off is probably a good thing so that other people aren't annoyed at you. Yeah. Oh yes. Oh yes. If the dog starts barking, there's nothing I could do about that. I know. There's a dog barking that started barking. What the nice thing is though, you should be able to turn down the volume on the computer so that it can be minimized, but don't turn it down all the way so that you can't hear any of the announcements. Yes, yes. Are we good to use our phones to scan in the last 10 minutes? Yes. Yeah. Okay. Yep, you should be allowed to. Do we need our mics on? Yes. Yes, you will need your mics on. So it should be in a quiet room. Yeah. The nice thing is though, you can maybe have a glass of water or something nearby. So. Excellent. Okay. So something like this, and then they'll be like using the definition of the derivative. And you guys can feel free. This is just kind of a review question or something like that to I can kind of do this without really thinking too much. So again, I can keep an eye on the chat. If there's any more questions about the test, what I would say is that the questions from the assignment are probably going to be very similar to kind of the questions I would ask on the test. So you should be doing the assignments. And hopefully with the quizzes pacing you, that it should have been motivating you to at least have worked through the questions. I have had some people email me asking, first of all, where's the textbook? Well, we have been using an online copy of a book for a while, and along with that online book, we have the solutions manual to it. So the solutions are available to all the odd questions. And what's the other? So I'm just substituting in those values. Essentially, I'm trying to make sure I get your money's worth, right up until the end. For this example, do we need to write limit delta x every single time? Yes. Why? Because we haven't taken it yet. So, yeah. Unfortunately, we do have to, because this is an operation that we're kind of postponing. What we're doing here is in this step, we've substituted in this step here, I'm just expanding. So I'm still just doing algebraic manipulations. I'm just distributing that negative. So I have a 3 and a minus 3. I have an x squared and an x squared. And still haven't taken the limit yet, so I have to write it again. So to answer your question, you write it every single time until you take that limit. So I have 2x delta x plus delta x squared still haven't taken it. Haven't taken that limit yet, Joe. So I'll factor this out. I have 2x plus delta x. That cancels. So now, no, I haven't taken the limit yet. Still not taking the limit, still there. So now I'm left with 2x plus delta x. If I wanted to be pedantic, I could apply using my limit rules. Maybe I'm just trying to, there we go. We're almost done. Now I can stop writing it because I'm going to actually take the limit. So the limit as delta x goes to 0 of 2x. So there's no delta x here, so I can just write that as 2x plus the limit as delta x goes to 0 of delta x. Well, that's just 0. And so now I'm done. So I got 2x from f of x is equal to x squared plus 3. And, with just using our quick rules of differentiating, we should know that the 2 comes down in front. That's good. Plus the 3. No, that's a constant, so that's equal to 0. Going back to limits a bit, it's like taking the long road and ignoring the derivative. Yes. Yep. Going back to limits is a bit like taking the long road and ignoring the derivative power rule shortcut. Well, the reason for we actually did prove it. We did prove that rule. Ta-da! Because we did it. There's the proposition. There's the power rule. And then we did the same thing. We used the definition of the derivative. We factored it. And then, because we were able to factor it, again, there's Joe, which he's like, do we have to write the limit? Yes, we haven't taken the derivative yet, or we haven't taken the limit there yet. So what we had to do was we factored it so that we could get that delta x out. So we got the delta x out and we were able to cancel it. And then at this point, right here, is where I could start. Can I move this up any further? Here we go. Nope. It's because it's still in the my binder here. Let's see. There we go. So at this point, here is when I started to apply the limit, and then I was able to simplify it. The question is, do we need to show the third last step you did? No. I'm good with you going from here to here. But I'm still just I'm just making sure. Actually, why I did that step was because I wanted to write out limit a couple more times just for Joe. So, but no, if you went from here to here, I'm okay with that. Okay, and that's time. Thank you everyone for tuning in for MAE 113. It does show knowledge of some of the rules of limits. Yep, it does. So if there's any other questions, feel free to send me an email. I'll be available to answer. The other thing I was going to say is that I'm going to do one office hour tomorrow. So that's office hour is going to be tomorrow from 12 Eastern Standard Time to 1 Eastern Standard Time. 1 p.m., not 1 a.m. Okay. And so if you have questions, concerns, again, email. You can come tomorrow to the office hour. I've already set it up on Moodle. Okay. Everyone, have a great evening. Enjoy your dinner. And hopefully I'll see some of you tomorrow. Take care.